Good afternoon, ladies and gentlemen. Together with my colleague Lukáš Venkrbec from College of Polytechnic Jihlava and me, my name is Květoslav Belda from Adaptive System Department, the Czech Academy of Sciences, Institute of Information Theory and Automation. We would like to present our contribution entitled Control Principles of Stationary Articulated Robots used in cyber-physical factories. So, outline of my presentation is the following. Firstly, I would like to speak about our motivation. I simply describe cyber physical factory, which we have in Jihlava. And also, I would like to speak something about articulated robots, manipulators, and its importance in just cyber physical factories. Then I will focus on mathematical model of robot kinematics. Then I will mention also mathematical model of robot dynamics. So this is complete description of the robot. And then I will show you several concepts and principles from conventional one to second advanced. So it means both are connected with cyber physical factories. And then I will focus on software tools suitable for data mining, data acquisition, as a source for identification and modeling, because in point 2 and 3 we use more or less ideal model from mathematical analysis, but from real point of view, we need real data, real parameters to be more precise for control design. So I will tell you something about software tools from Mathworks company, Simscape library, and robotic system toolbox. And then I will say you several words about RT toolbox from Mitsubishi Electric company. And then I will show you real experiments or real measurements just using RT toolbox from Mitsubishi Electric as a source data for identification. So my motivation also with my colleagues is today very often mention word industry 4. So the concept of the industry you can see on the left side, smart entities, so it means robots, buildings, and so on. These entities are equipped by sensors and drives to be move, to be actuated, and also to have a sense to obtain information from their surroundings. And also very important property is collaboration, humans and artificial intelligence and real robots or another devices. Very important point is networking. So all components are set in nets, and also we should take into account big data. So we should collect the information from any sensors and make some analysis and so on. And a very important point is virtualization. So today somebody mentioned that mass production moved to customizer production. That's true. So it means that all tool should have information about what you can do, and also information from the product, what the product needs to be to be produced or something like that. So here you can see example of one specific factory, and this is connected with some production line and individual modules. And here you can see example just of one module. It's assembly module, and this is real photo from our factory. I make only one small part, because this is also for future for next presentations. But you can imagine that we have a very real robot uh, from Mitsubishi Electric, and here you can see it with description of the coordinates. So there are 6 axes, 1, 2, 3, 4, 5, 6. So this robot has 6 degrees of freedom, and tool center point at the end. You can see also 6 degrees of freedom, motion in axis X, Y, and Z, and rotation around these axes. So this is very important for modeling, because these coordinates more or less form the mathematical model. So, as I mentioned, I would like to speak several words about mathematical model of robot kinematics. This is standard task. There is two problems: forward problem and inverse problem. So it means that at the beginning, if you have angles in individual joints, you can compute directly tool center point. It means this an effector position. An inverse problem, it's opposite, and also it's more or less difficult, that you have only endpoint, and you should compute individual rotations in joints. So where I mentioned this, every producer of the robots has a specific selection of the coordinates. So somebody can say, okay, this is simple question, but firstly you should do a real deep analysis and to obtain adequate information, because if you take data from some software, you don't have really joints orientation in one situation. So if you have more or less the similar situation, so different is in Kuka's company or in Mitsubishi Electric and so on. So this is important to obtain such analysis. And then for forward problem, you can use standard transformation matrix in such form based on specific approach. And for this matrix, you should select parameters according to just your analysis to obtain adequate transformation matrices. So because we have 6 degrees of freedom, we need more or less 6, 7 such matrices. I said 7 because there is also another part in the wrist. And by this chain, you can directly solve this forward problem. It means that you substitute only individual coordinates, rotation angle, and each such matrix represent this type of matrix and with appropriate index of the joint. And on other side, inverse problem is more complicated. There is no exactly forward solution. It's possible to use some numerical solution, but it's not more or less analytic, but because we search for analytic solution, because it's more or less quicker than numerical solution. So here you can see some geometric formulas based on this geometry, and you can compute individual coordinates in individual joints. And also, if you provide time derivative of this expression, you obtain also information about speed and acceleration. Second model, which really connected and related with kinematic one, it's mathematical model of robot dynamics. Standard situation, so from Lagrange equation of second order, you can provide equations of motion, and you use information about kinetic energy and potential energy. We should take into account potential energy because our articulated robot is not in one plane, but is in general three-dimensional space. And by application of this formula with this prescription of kinematic energy and potential energy, you obtain these equations of motions. And as you see, there is only mathematical transformation. If you have at the beginning torques, you can compute joints and information about joints and also tool center point. This is forward problem. And inverse problem, this is opposite task, more or less control task. You have all coordinates and you should compute torque. It means not only one, but 6 torques for 6 joints. Here now I would like to continue with the main point of my presentation. Also, the first point, main point of my presentation: control concept and principles. Standardly in robotics, you can see such type conventional cascade control. So it means on each drive you have such control structure. So it means you have 6 standard structures like here with position loop, speed loop, current loop, and power converter and actuator or drive. So this is standard, more or less we can say that is okay, but this concept is more or less on the border of improvements because there are a lot of another supporting blocks, but the structure is more or less fixed. Therefore, it's important to start or to do also different approach. Just because I mentioned model of kinematics and dynamics. Therefore, I focus on model predictive controls. This is one example of model-based control design. So there is specific concept. So it means that we can remove the such structure and something add. So it means that we can optimize motion of the robot from physical point of view, from construction of the robot. So this is more or less this global model predictive control, and from this we obtain reference force effects as a feed forward for local model predictive control applied on drives. So it means that this one conventional cascade control for one joint we remove by local model predictive control with all features, but with small possibilities how to optimize control process. And moreover, we have also information about motion of individual parts of the robot. So it means that there is more information in opposite to here, because real structure of the robot in this concept, in conventional concept, this is only disturbance without any in relations to control design. So this is the main idea, that we can remove this position by model predictive control of mechanical system which generates reference force torques or force effects, and several local drives control model predictive control for the drives. So we have for our case 6 model predictive control on local level and 1 global model predictive control for mechanical system. And you can see also some feedbacks, local feedbacks and global feedback. And all is given by measurements from motor side. Now I would like to continue with software tools. As I mentioned, today there are a lot of software tools how to provide simply modeling without mathematical background. It is very good for simulation, but for real control, you need still something, write some equations and make derivation of these equations. But for the fast prototyping and so on, it's important. So here you can see one example of SimScape multibody library. So it means that you download 3D model and provide some modifications, and you obtain some simple structure. Here you can see six joints, but what is around you should add. So it means that it's not so simple task, but at the beginning you push only one button and you obtain this initial structure with uh, simple visualization. Another more scientific approach is use robotic system toolbox, which can be provided directly in simple MATLAB without simulating, and you can download individual bodies of the robot and provide also simulations. An advantage is that you can also visualize trajectory of the robot. So in this type of SimScape multiple library, it's not possible. Here it's information about trajectory. There is also um, somebody mentioned difficulty of transformation between machining tools and robotics. So G code, which describe directly main parameters of trajectory, can be used as well, but you should provide some interface to obtain adequate planning from shape and time parameterization. Another software, it's more or less from uh, industrial side. It's RT toolbox from Mitsubishi Electric Company. So there are also some description of the trajectory, but you can see it that is a little bit different. Mitsubishi Electric use specific Melfa language, which more or less the same like G code, but with some different labels and commands, and it's a little bit longer, but the result is the same. Here you have the same description as here. So for G code, it's only here, and for Malfayasic, you need this code and this definition of the trajectories. And you can provide such motion, and on next slide you will see the results. So this is real measurements using this RT toolbox for selected trajectory, and you can see it reference values, and here it's feedback. So it means that for first view this is the more or less the same, it's okay, but from this picture, this is the current loop, you can see exactly which joint is the most important for the motion. It's joint 2 because it moves with the robot for the whole motion, uh, and makes the whole motion of this, and another axes are only supportive for the motion or have no relation to effects of gravitation. So I would like to conclude my work. Modeling, mathematical modeling or mathematical models, it's better word. Mathematical models should be adapted to a specific industrial robot, as I already mentioned. Uh, I presented conventional control and advanced hierarchical control concept. And I showed representative of possible software tools for modeling, generating data, measurement and simulation, for identifying and verifying model parameters. So it means, for example, moment of inertia, weights, and so on, because the length can be measured simply by standard ruler. And all pictures were captured on assembly module in Cyber Physical Factory at College of Polytechnic of Jihlava. So thank you very much for your attention. And if you have a question, you can put now or during next days.